Hello, here we're on our second physics video for modern physics. Today we're going to look at mass energy equivalence. Now I know you've done E equals mc squared in chemistry, but we're going to take a different approach. And I'm going to sort of come at it from a physics point of view of what it really means, and we're going to derive it, right? And we're going to look at the full equation. So let's go back a bit, and let's start with something we know, which I spent one lesson teaching you the whole unit, momentum. All right, now let's say we have a head-on collision. Now in this case, these two balls have the exact same mass. They move towards each other with some speed v, the exact same speed v, then they collide, and after the collision, they move away at the same speed v. Knowing that, and based on momentum conservation, what can you say about the two masses? They would be the same, wouldn't they? Okay, so, all right, let's go into another one. Now let's say these two balls move towards each other at a speed v, but after they collide, one moves away at the same speed while the other's speed has increased. What can you say about the two masses? Definitely one of them is bigger than the other. Which one's the larger mass? Yeah. Okay, so the top one will be the larger mass. Okay, and then we look at our last scenario, where we've got one ball moving down at a small speed v and one ball moving up at a large speed v. And when they collide, they move apart at the same speeds that they started with. So the fast one's still moving fast and the small one's still moving fast. What can you say about their masses? Well, in this case, the above one would have a larger mass, but also there would be a nice ratio there. And I do go over more of a derivation of that in another video, so please look at that video later. All right, now let's look at this example. Here we have Alice and Bob. Now they're both moving sideways at some speed v, and they also have a vertical speed. And as they approach the center, that dotted line, they hit and bounce off. Now their vertical speeds are identical, and after they hit and bounce off, right, again, their vertical speeds are identical. So what could you say about the masses of Alice and Bob? You would say they're the same, right? Just like our first example on the previous page. But let's do something else. Let's say now that Bob is moving, or Alice is moving. One of them is moving very, very fast. Okay, close to the speed of light. So now what we're going to do is we're going to be an observer running next to Bob. So we're going to run next to Bob. And so from our point of view, it just looked like Bob is going up and back, right? And slowly too. So Bob's speed is nowhere near the speed of light. From our point of view anyways. It's Alice's speed, her horizontal speed anyways, that is moving very, very fast, close to the speed of light. Now her vertical speed is not relativistic at all. It's moving fairly slowly for our standards. Okay, now what happens? Well, time dilation is going to occur. Now before, they were moving at the same vertical speed, so they would approach that center line at the same amount of time and then move away. Now let's say, for example, it takes Bob 3 seconds to get to that center line. From Bob's point of view, how long does it take Alice to get to that center point of line? She's moving very, very, very fast. Now from Alice's point of view, she's not, and she would move towards that center of line in 3 seconds. But from Bob's point of view, how long would it take? Okay, I accidentally paused the video, but I want you to pause the video, not me, and think about it. How long would it take Alice to reach that center line from Bob's point of view? Now, because of time dilation, it'll take more time, maybe, I don't know, 5 seconds. So from Bob's point of view, it's taking Alice 5 seconds to reach that center line because she's moving so fast horizontally. If it's taking her 5 seconds to reach that center point of line, it seems like she's moving slower than Bob is, vertically anyways, because they have to travel the same distance, but Alice is taking longer to do it. So now we have Alice, let's just look at the vertical components now, moving slower towards that center line and moving away at that same speed v, whereas Bob is moving faster. So now here's my question. What can you say about the masses of Alice and Bob? They're not the same anymore, are they? Right? Alice's mass appears to be greater, or at least it's harder to deflect her motion. So what we say is her effective inertia has increased due to time dilation and sideways inertia as well. And we can write this as her effective inertia, capital M, equals that Lorentz factor, which we know, times small m, her rest mass. All right, now let's move aside for a little bit and let's do a separate thought experiment. We're going to be doing a lot of thought experiments, so kind of, I usually like to ask questions during this lesson, but just try to think as we're going through this. All right, here we have a box. This is not Schrodinger's box or Schrodinger's cat. That'll be another day. This is just a box. Now the box is closed. We don't know what's inside the box. But you measure the box and it has some mass m. Now sometime later, nothing happens to the box. No one's opened it. No one's put anything into it. Nothing's happened to the box. At some time later, what could you say about the mass of that box? It would be the same, wouldn't it? I'm not trying to trick you or anything. The mass of the box would be the same, so m equals m prime. All right, now let's say that box is originally moving up at some speed v. Doesn't really matter what the speed is, as long as it's less than c. But it's moving up at the speed v. And then sometime later, it's still moving up at the same speed v. What could you say about the masses of that box? Has it changed? Well, no, it hasn't changed at all. It's the same. Still not trying to trick you. Okay. Now we open that box. And inside the box, this is what we see. We see two masses moving apart due to a spring. Now, this is an amazing spring because these two masses are moving apart at almost the speed of light. So what have we just learned here? If the mass of that box is never changing, well, as it's moving away at almost the speed of light, it must have some effective inertia. Right? That means kinetic energy has some sort of effective inertia. Well, that's interesting, but what's going to happen is it's not going to go outwards forever. It's going to actually come to a complete stop. There's no more effective inertia due to time dilation. But the mass has never changed. And so even though there's no effective inertia due to time dilation, the mass hasn't changed, which means there must be some kind of effective inertia inside potential energy as well. Okay, now we talked about energy in grade 11, we talked about it in grade 12. We define it as the ability to do work. Okay, well, really, what is energy? What do they all have in common? Well, it looks like both kinetic energy and potential energy have inertia. Okay, that's new. Let's just move on here. Now let's say the brick is made up of atoms. Okay, again, new thought experiment. We have a brick. It's made up of atoms, and those atoms are connected by these interatomic bonds, which are like spring-like. They're going like this. Okay, now as the brick is heated, right, from kinetic molecular theory, what would you expect its mass to happen? Would it increase? As it's heated, you have more kinetic energy. If you have more kinetic energy, you have more inertia. right? Similarly, potential energy, your total energy of the whole system is increased, so you have more inertia. So yes, the mass would increase. Now you're not going to go to a chemistry lab and actually measure that increase of mass on a double band balance. It's going to be a small increase, but it's still increasing. Next, all right, next thought experiment. So inside of this box, we have a brick of mass m. We also have 2 photons of light. And those 2 photons of light hit the brick and get absorbed. And so now the brick's mass is m prime. Now that whole box that contains the brick, you've already said, well, I'm assuming you've said, but we've already gone over that the mass of that entire box does not change. Well, but we also know the mass of that brick increases. So does that mean light has mass? No. Be very careful. Mass has inertia. Kinetic energy has inertia, but that doesn't mean kinetic energy is mass. It's just they have a similar property. Okay? Mass is directly related to inertia. It's directly proportional to inertia. The more mass you have, the more inertia you have. But that doesn't mean they're the same thing. A lot of students usually get confused with that. They think inertia is mass. No, no. Mass has inertia. Mass is not inertia. It has inertia. Kinetic energy has inertia. Potential energy has inertia. And now, based on what we've looked at this experiment, light also has inertia, not mass. All right? All right, so this is a really interesting property that everything seems to have in common. It's hard to describe exactly what energy is, but the fact that all energy seems to have one thing in common, inertia, is quite powerful. But what about rest mass? Okay, now I said that mass has inertia, but is it just because mass has energy? What about mass that's at rest? Completely at rest, does it have energy? Well, let's try this thought experiment. So we have a box, and we're going to put 2 particles in the box. One particle and its antiparticle, called antimatter. Now it could be an electron and a positron if you wish. Now I think I went over antimatter a little bit in grade 11, but let me just do a recap. So for example, if you were to have a hydrogen atom. A hydrogen atom has what? It has a proton in the nucleus and an electron in orbit. You could have an anti-hydrogen atom, in which case it would have an anti-proton, the exact same mass as a proton, but opposite charge. And in orbit, you would have a positron, the exact same mass, but opposite charge. Now these do exist. We have observed them, and we can even create them. But the problem is storing them. It's hard to store because the instant they touch each other, when matter and antimatter touch, they completely 100% annihilate each other, producing only energy. Okay, so in this case, in our box, what we've done is set up well, a disaster that's about to happen. Luckily, it's only one particle and antiparticle, so we're not going to blow up the city or anything. But we have, let's say, an electron and a positron. When they touch, they initially have mass, but when they touch, all that mass is gone. And let's say we get 2 photons, each with a certain amount of energy. Wait, those photons have inertia. And if those photons have inertia, well, the mass of that entire box hasn't changed. That must mean the mass of the particles before must have some kind of energy. Right? Even just at rest, mass itself must have energy. Right? Because that energy appears to be gone, but it can't. Okay, so yes, rest mass has energy. And putting everything together, now this is very important, we get E equals mc squared. But it's not just rest mass that has energy, right? It's not just rest mass. All energy has inertia, mass has inertia, right? They're all the same thing. Now in this equation, when you set one equals to each other, a lot of times people says one is converted to another. No, they're not converted into each other. They're the same thing, right? It's no different than saying kinetic energy transfers into potential energy. Mass transfers into energy. Think of mass as a condensed form of energy, because when you take enough energy and you condense it to a small enough point, you create matter or mass. Now another thing, notice we have that gamma factor in there. Why do we have the gamma factor in there? Because E equals mc squared only works when the velocity of your particle is 0. Right? It's a very specific situation. Right? Now that can be expanded to this formula, and I do go over the derivation of how you expand it in my other video. Also, question 1 on the back of the sheet tries to lead you through how to derive E equals mc squared, and then from that how to get this full equation with your gamma factor. Try going through that question 1 yourself, but if you get stuck, watch my other video. It'll be posted. All right, but we have E squared equals m squared c to the 4, or just mc squared all squared, plus pc, your momentum, all squared. Okay, remember that P is relativistic momentum, which is gamma mv. All right, now let's look at, I'm going to go over this equation a little bit more when we get to quantum mechanics. But let's say you have no mass. Well, it looks like, if you were to just look at this equation, or if you just look at E equals mc squared, it looks like if you have no mass, you have no energy. Right? And if you look at momentum, well, momentum has the mass term inside of it. But very important, photons can also have momentum. They have inertia, and therefore they also have momentum. That momentum you cannot calculate by just writing mv, because they don't have mass. So the momentum for a photon of light is calculated with the equation h over lambda, where lambda is the wavelength of that photon of light, and h is Planck's constant, which we will go over next week in our lessons on quantum mechanics. All right, so let's go over the question on the back. Question on the back says, the sun provides the energy that is the basis for virtually every food chain. We measure the energy output of the sun by its luminosity and find that the sun emits 3.8 times 10 to the 26 watts. Okay, if you don't remember watts, remember it's work over time, so joules per second. Use E equals mc squared to determine how much mass the sun is losing every second. All right. Let's do this on the whiteboard. I'm going to make this a bit bigger. There we go. So first question, use E equals mc squared to determine how much mass the sun is losing every second. Well, every second, the sun loses this much mass. I've just already rearranged the equation because that's not a difficult equation. And when we plug in the energy, it's 3.8 times 10 to the 26 joules over c squared meters per second. And that's every second. And when we plug that into our calculator, we get 4.2 times 10 to the 9 kilograms every second. So the sun loses 4.2 billion kilograms every second. Usually students freak out when they hear that. Oh, we don't have much time left. No, don't worry. Let's actually look at part 2. It says the sun's total mass is 2 times 10 to the 30 kilograms. Now, if the sun were to use up all its mass, that wouldn't happen in the life cycle of a star, but let's just say it uses up all its mass. How long would it take? All right. Well, let's take this value here, which is what it loses every second, and divide that by how much mass we actually have. Oh no, sorry. Total mass, which is 2 times 10 to the 30 kilograms. So that's how much it has, and this is how much it loses every second. And so it would take 4.7 times 10 to the 30 seconds. 30? Can't read my own writing. I think I wrote 20. All right, well then, how many years is that? We'll divide by 60, divide by 60 again, and then we got 24 hours in a day, 365 days in a year. So keep dividing and you'll get 1.5 times 10 to the 13 years. That's just how massive our sun actually is. Okay, well, actually our sun's only going to last about another 5 billion years. It's middle-aged right now. So after 5 billion years, how much of its mass has actually, what percent of its mass has actually been destroyed to produce energy? Well, to do that, we got 5 billion years. And let's look at that as a percentage of 1.5 times 10 to the 13, how much we would have to completely get rid of everything, times 100%. That's wrong. Whoops. Okay, so to figure out the ratio of mass loss then, and I just put in years because the ratio of years will be the same as the ratio of mass loss because mass, according to our calculations, is being lost at a constant rate. Okay? In reality, that's not true, but we're not going to go over the whole stellar evolution of a star right now. Okay, it's going to be 0.033%. It's losing very little. It's losing a lot of mass, but very little of its mass over the course of its life. Okay. So that'll be it. I'm going to post a couple other videos, one of mine where I go over the derivation and how we do question 1, and then a couple other videos which are also good to try and get a better understanding of E equals mc squared. All right.